Hi there, I'd like to do a fairly short lesson on our Earth's oceans, the hydrosphere, and specifically about the energy absorption of all of that water within our atmosphere and within the oceans. So let's take a look at this as the world turns. So we obviously live on this big giant globy thingy that has a lot of water at the surface. And something that needs to be recognized is that as the sun's rays come beaming down to us, that the surface of the water is going to absorb quite a lot of the sun's rays. So they kind of come in, some of it bounces off, but a good portion gets absorbed by the water. And that is something that I'd like to focus on for a moment. Now, it's not so simple as to say that the oceans warm up, they absorb energy, and the temperatures of the oceans rise. It's not quite so simple, partly because there are different zones to the ocean as you look at the depth of the oceans. So the water doesn't fully mix so easily, so you have the top portion that will warm up a little bit more than the bottom portion, quite obviously. And you have different layers of the ocean, and there's different convection currents that occur. Remember that convection currents are currents that occur where there is the warm air or warm water will rise, and cold air or cold water will go down. And so those convection currents can and do in fact happen in the oceans. And so if we were to even take a look at that, if I can actually diagram that real briefly, let's choose a color that makes sense. So you have, let's say for example, if I were to just express that this is like the equator kind of area, let's say that this is like a north-south sort of space. Doesn't fully make great sense in my example, but it's just going to have to. So let's say this is the equator. So this part is being warmed up more than this part. So let's just say that this area over here is there's no palm trees there. Let's just say that this is the Arctic or something like that. And so what you'll have happen is the ocean water here will get warmed up, right? So it's going to kind of encourage water from here to rise. You will have a spread of water along the top, and then at some point you'll have water cool down, and we'll express that with a blue color. Maybe you'll see it, not too well, but still. So you'll have some water that's going across, and then of course it will start to heat up as it gets towards the surface, and you have these convection cells that kind of move around in circles. And it allows some flow, but it only goes so deep and things like that. So the ocean is a fairly complex thing. It is dynamic, it is changing, and there is of course the ocean currents that will have these convection currents. But viewed from the top, there's also currents that happen driven by the convection currents, but these ocean currents viewed from the top will also flow in these ways. So this is why Europe tends to be a bit warmer than it would be otherwise. So if we were to take a look at the latitude of Europe compared to Ohio, southern, actually I think I have this moved slightly, there we go. So that's, whoops, let's try that again. So we've got Ohio, which isn't really any farther north than Italy. They're pretty similar latitudes. But why is it that Italy tends to be a warmer climate? It's because of these ocean currents driving and really bringing these currents farther inland because of the way that they drive in. So by having a change in temperature of the oceans, these currents will change, and that is something that I'll take a look at here. So let's take a look at what's driving these things to change. So let's kind of recap that idea of the greenhouse effect. So the greenhouse effect is where the sun rays are coming in through the atmosphere. Some of it will bounce off, specifically off of certain parts of the atmosphere, off of clouds, and specifically very much off of ice. So at the poles, the North and South Pole, where there's a lot of white ice, it's white because it's reflecting a lot of light, and it causes quite a lot of energy reflection, and a lot of that energy will be reflected off into space, which kind of is a good thing when it comes to global warming effects. However, if this ice disappears, then more of the energy will be absorbed by the Earth and by the oceans. Some of that energy that enters will be re-emitted at typically a longer wavelength. So red is going to actually is a longer wavelength color, so it's kind of represented by that these red arrows, and that longer wavelength typically will get trapped by layers of the atmosphere. So we have three different, and it's not just limited to this, but three main drivers of the greenhouse effect. Okay, they're known as global warming gases, and there's other gases that have global warming effects as well. And then there's the ozone layer, and that's a whole nother issue with CFCs. But let's look at the big drivers of the greenhouse effect. So water vapor is a massive driver of the greenhouse effect. So it is water vapor in the atmosphere will cause this reflection back down towards Earth of heat energy. And in fact, most of the greenhouse effect that happens on Earth happens because of water vapor. And that's a good thing. We like a nice warm climate. There's a certain sweet spot. We don't want it too cold. We don't want it too warm. We don't want it quite balmy either. So we want it at this nice sweet spot sort of level. Methane is a global warming gas. In fact, it is a 10 times more global warming gas than CO2 is in terms of its effect. Per molecule, methane has a greater reflective effect, reflecting the energy back down towards the Earth. And so methane is essentially what you get from cow byproducts. Let's put it that way. Methane escapes from deep inside of the Earth. That's what natural gas is. And natural gas is basically just the decomposition of organic material, which is pretty much what the leftover stuff is from cows. And as you can imagine, actually cows themselves are a bit of an issue when it comes to methane and global warming issues, and there are ways around that. In fact, rather than just allowing the methane to be expelled from all of the poop that's all around, instead you can actually trap that gas that's being expelled, not directly from the cow, but from their excrement, and you can actually trap those gases and you can burn it. Now you do get CO2, however, since CO2 is less of a global warming gas than methane is, you actually have a positive effect from a environmental aspect. The downside to CO2, in comparison to methane, is that I do believe it stays in the atmosphere longer, if I'm not mistaken. So CO2 is the thing that we really talk about mostly because that is the product. It's not that it's a greater factor in terms of per molecule than these two. It's just that this is the one that we specifically are really pumping a lot of into the atmosphere, and so we are creating this addition. Water vapor is a huge global warming contributor. However, it's naturally occurring all the time. CO2 is too, but water vapor's just, it's everywhere, right? And it's got good benefits to the atmosphere. And we are not pumping huge amounts of water vapor into the atmosphere, not directly. That's more of an indirect effect, which I can get into in a moment. It's the CO2 that we are pumping directly into the atmosphere by way of our cars, by way of our power plants, of any coal burning or gas power plants, those kinds of things. And so CO2 is that driver, and it is going to reflect the energy back down towards the Earth. And what is it going to do? It's going to warm up the Earth. It's going to warm up the oceans. And then what's going to happen? Those oceans are going to evaporate a little bit. So you're going to get more water vapor into the atmosphere, which then in turn does what? It reflects more energy down towards the Earth, which warms up the oceans, which does what? It creates more water vapor, which then in turn also melts some of the oceans, which then causes the water to heat up more because it's absorbing more energy. And then it also causes permafrost to thaw, which releases methane, which then oh my. So that's known as a feedback loop, where this compounding effect continues to happen, and that's where we are right now. Let's take a look at the energy that water absorbs. So I'm going to get a little bit, technical on you here. I'm not going to go too much into like math exactly, but let's take a look at some, sort of physical processes of water, properties of water, I should say. So for water has, and of course as a physics person I'm going to express these these things in these units. These are the SI units. So as a physics person, I always express them in these units. But for water, water has a specific heat of 4,180 joules per kilogram times Celsius. What the heck does that mean? That means that if you had 1 kilogram of water, so I'm just going to give you a shape here. Let's just say that we have this container filled with water. If I can express that. So I have this container filled with water, and it's 1 kilogram. So it's just a pot of water essentially. And the water is, I don't know, let's just say it's 50 degrees Celsius, okay? So it's warm water, don't get me wrong. And I want to raise the temperature of this 1 kilogram, right? This is 1 kilogram of water. I want to raise the temperature of this 1 kilogram of water from 50 up to 51 degrees Celsius. Sorry about my one, really too large. But how much energy would it take to raise the 1 kilogram of water by 1 degree Celsius? It would take 4,180 joules to do that. Okay. Now, without context, that's really difficult to understand what that means. Basically, this number is extremely large in comparison to most other materials. For aluminum, it has a specific heat of, I think, like 903 joules per kilogram, which means that if you have 1 kilogram of aluminum, it takes 4 times less energy to heat up that aluminum by that 1 degree Celsius. Or what about air? Okay, so I have this as a comparison. What about the atmosphere around us? If I have 1 kilogram of air, yes, obviously it takes up more space, but still, if I had 1 kilogram of air and I wanted to heat up that 1 kilogram of air, it would take just over 1,000 joules of energy to heat up that 1 kilogram of air. So again, it requires 4 times more energy to heat up 1 kilogram of water than in comparison to 1 kilogram of air. So why is that relevant? Because as the energy comes in from the sun and it hits the air, it hits the oceans, if the atmosphere around us raises in temperature by 1 degree Celsius, and the oceans also raise in temperature by 1 degree Celsius, do you recognize that, let's say that the mass of the two things are the same, the mass of the oceans and the mass of the air in the atmosphere is the same. If the ocean were to raise in temperature by the same as the air, it must have taken 4 times more energy. So the Earth is a heat sink. It has the ability to absorb, the oceans are the heat sink, excuse me, and so they have the ability to absorb a lot of energy before raising in temperature. So this means that if the oceans raise in temperature, and they are, that's why we have bleaching of coral reefs. If the oceans raise in temperature by anything that we can measure that is remotely significant, then that means that the oceans absorbed a huge amount of energy. And it is not something that we are taking very much notice of, because it doesn't seem like a lot of increase in temperature for us. However, that's a lot of energy that then can be dissipated elsewhere. So let's take a look at what the mass is between the atmosphere and all of the oceans and lakes and things like that. So the atmosphere mass, this is 5.1 times 10 to the 18th kilograms, and the hydrosphere mass is 1.4 times 10 to the 21st kilograms. This is for the entire Earth. So this number here is just about 300 times larger than this number here. So if the oceans heat up by a little bit, not only do they have the ability to absorb 4 times more energy than the air before it raises it by 1 degree Celsius, but there's also almost 300 times more mass for it to be able to absorb. That means that if the oceans increase by temperature, their temperature by just a little bit, it's a huge change. But wait, there's more. So heat of fusion and heat of vaporization, these are latent heats. So what this means is that if I wanted to take this 1 kilogram of water, so let's say we get this 1 kilogram of water, let's say we get it up to to 100 degrees Celsius. And you guys should know that water boils at 100 degrees Celsius, right? At 1 atmosphere pressure and all that thing. So we get it up to 100 degrees Celsius. And it's now going to boil, okay? So we're gonna boil off this water. So I'm gonna take this whole kilogram of water, I'm just gonna heat it up and boil it all off until the whole thing's gone, right? If you've ever, tried to, reduce down a soup or something like that, you might understand where I'm going with that. So, heat of vaporization, the heat of vaporization, if I wanted to evaporate all of this 1 kilogram of water, right? So it's not increasing in temperature. By the way, it's not, so as the molecules go off in their evaporated state, they're still at 100 degrees Celsius. So here's the bits of water vapor, right? They are still at 100 degrees Celsius. They've just gained energy just because they have changed their physical state. So how much energy does it take, this 1 kilogram of water, and convert it into 1 kilogram of water vapor? Look at how much energy this is. So when the oceans cause evaporation, right? So I had talked about the oceans, right? The sun coming down and it causes more evaporation, right? So they're not boiling, obviously, but we are causing more evaporation because the warmer the oceans are, the more water vapor will be expelled, right? The more likely water molecules are to be left into the gas phase. Plus, the more ability the atmosphere has of retaining moisture. Warm air can hold more moisture than cold air. You have probably noticed that because, as it gets cold, your skin dries out in the winter. At least mine does. And so this is over 2 million joules of energy per gallon. So it would take 2 million joules of energy to take that whole thing and turn it into water vapor, which is why if you wanted to try and boil off a pot of water, it takes a really long time to do. The heat of fusion is to take this kilogram of water, if it was, let's say we bring it down to 0 degrees Celsius, right? So we bring it down to 0 degrees Celsius and I want to make it a block of ice. It would take this much energy to make it a block of ice, or the other way around, to take a block of ice and turn it into liquid water. So this is a huge, wait a minute, 334,000 joules, right? I said this was a big number. Holy cow, that's still big, right? So what does that mean? That means that for the oceans, right, or glaciers, if we have these glaciers, in order to melt all of this, that takes, for every kilogram that we're melting, not even changing the temperature of it, we are just in the melting process, it takes 334,000 joules of energy to melt each kilogram of it. So without even increasing the temperature, when we see that the glaciers are melting, that is a massive amount of energy absorption. If we get to the point where the glaciers melt, then the energy is no longer going to be going into the phase change. Instead, all of the energy is going to go straight into raising temperature. So you have these glaciers that are creating this delayed effect of temperature increase, right? They're absorbing energy and not allowing the temperature to increase. So instead, we just see the phase change. So when you see ice melting, that is not a good sign. It takes a huge amount of energy to change that phase. And so this just expresses the change in phase and the energy that it takes to go raise in temperature, change in phase, raise in temperature. So I hope that you understand that as we increase the temperature of the oceans, right, let me go back down. As we increase the temperature of the oceans, as we melt glaciers, as water vapor is put into the air due to these temperature increases, this is a huge amount of energy that is being absorbed. So while you might not recognize a very large temperature increase, when people say that the global temperatures have increased, they're usually talking about air. But I really don't like that they talk about air temperatures. Instead, we should be focusing on glacial melt, and we should be focusing on ocean temperatures, because that is where all of the energy is going. Take a look. Since 1970, oceans have absorbed more than 90% of the excess energy that we have created that has been trapped by CO2. More than 90%. And so the energy being trapped by the oceans, it is a massive heat sink. And I really want you guys to understand that when we talk about the Paris Climate Agreement that tries to limit the temperature increase of the globe by 1.5 degrees Celsius in the next so many years, they're just looking at the air temperatures. But that only matters so much because there's other issues at hand. Even if we keep the temperature the same, if glaciers are melting, we are still absorbing far more energy than we are emitting, and that is still a problem. So there is more to consider than just temperature, and the hydrosphere is a huge thing to consider because it is a giant heat sink for energy. It can absorb massive amounts of energy. Please pay attention to the phase change of the glaciers, to the water vapor that is being expelled into the atmosphere. Those are the things to focus on. I hope that this increases your knowledge on this concept, and that you have a little bit more appreciation for how much energy is actually being absorbed by the Earth, and it's mostly by the oceans. So please pay attention to those kinds of things. When they talk about glacial melt, it is not just a small deal. It is a huge deal. You guys have a good one. Not to put a damper on you, but you guys have a good one, and please educate yourself, read up more, and I'll talk to you guys next time. Take care.